Stars have always captured our imagination. They are the brilliant jewels of the night sky, scattered across the vast cosmic canvas, twinkling not because they flicker, but because their light has danced through layers of our atmosphere before reaching our eyes. From Earth, they appear silent and eternal. But beneath their serene glow lies a roaring furnace, an engine of creation and destruction. Through violent thermonuclear fusion, stars shine with staggering power, radiating energy that warms planets, shapes galaxies, and breathes life into the very atoms that make us. And yet, even after centuries of stargazing and decades of space exploration, the story of stars is far from over. In this episode, we will not just revisit the familiar lives of stars like our Sun or the violent deaths of supernovae. Instead, we will venture deeper into the theoretical edges of astrophysics, where strange objects are said to exist. Stars unlike anything we have ever observed. Some of them are so dense, so bizarre, they might mimic black holes. Others may be built not from matter, but from vacuum itself. Join me as we begin a journey into the mysterious world of exotic stars. To truly understand the exotic stars that challenge our imagination, we first need to understand how ordinary stars work. A star is not a solid object. It is an immense sphere of hot, ionized gas, what physicists call plasma. The Sun, for example, has no surface to stand on. If you were to fall toward it, you would not land. You would keep sinking deeper and deeper into increasingly hot and dense layers of gas. And yet, for all its chaos, the Sun does not collapse under its own weight. What keeps it stable? The answer lies in a cosmic tug-of-war between gravity and pressure. Gravity pulls everything inward, trying to compress the star into a smaller and denser form. But the core of the star fights back. Deep inside, nuclear fusion reactions convert hydrogen into helium, releasing tremendous amounts of energy in the form of light and heat. This radiation exerts pressure, an outward push, that counters the inward pull of gravity. In stars like the Sun, this delicate balance is what keeps them from imploding. The light you see from the Sun is not just illumination. It is a byproduct of the very force that holds the Sun up against its own immense gravity. This state of equilibrium is not just a feature of the Sun. It is a defining trait of all stable stars. The key difference between different types of stars lies in the source of their internal pressure. In young stars, fusion of hydrogen is the dominant force. As the star ages and runs out of hydrogen, it begins fusing helium and, in larger stars, even heavier elements like carbon, oxygen, and beyond. With each new fuel source, the type and intensity of internal pressure change. But no matter the process, the goal is always the same: to maintain balance against the star's relentless gravitational collapse. However, this balance cannot last forever. Eventually, a star exhausts all of its usable fuel. When that happens, the fusion reactions that once pushed outward cease, and gravity begins to win. Depending on the star's mass, the result may be a white dwarf, a neutron star, or even a black hole. But even in those stellar remnants, a new kind of pressure emerges, one that comes not from heat or fusion, but from the quantum properties of particles themselves. These forms of pressure are stranger, less intuitive, but just as important in keeping matter from collapsing entirely. So when we talk about stars, we are really talking about equilibrium, about the unseen war between collapse and resistance. Every point of light in the night sky is a reminder of this cosmic struggle. Stars exist because the outward energy from their cores can push back against their own immense weight. When that energy runs out, gravity takes over. This is the basic physics behind stellar structure, the principle that governs both the most familiar stars and the strangest objects we will explore. And now that we understand the rules of ordinary stars, we are ready to break them. The sun is the most important star in our lives, not just because it lights our days and warms our world, but because it is also the best studied star in the universe. Through it, we have come to understand the lives of countless other stars. Right now, our sun is in the middle of its life, quietly fusing hydrogen into helium in its core. This stage, called the main sequence, lasts for billions of years and represents the most stable phase in a star's existence. But like all things in the universe, the sun's stability is temporary. Its time as a hydrogen-burning star will eventually run out. In roughly 5 billion years, the sun will deplete the hydrogen in its core. With no more hydrogen to fuse, the delicate balance between radiation pressure and gravity will begin to break. The core will start to collapse under its own weight, and this collapse will heat up the surrounding layers, causing them to expand dramatically. The sun will balloon into a red giant, growing so large that it may engulf the orbits of Mercury, Venus, and possibly even Earth. From the outside, it will appear cooler and redder, but inside, helium fusion will ignite, producing heavier elements like carbon and oxygen. This red giant phase will not last forever. Once the sun exhausts its supply of helium, it will no longer be able to generate enough pressure to hold up its massive outer layers. These layers will be ejected into space, forming a beautiful shell of glowing gas, known as a planetary nebula. What remains at the center is the sun's core, now a dense, hot object roughly the size of Earth, called a white dwarf. It will no longer shine by fusion, but by the residual heat trapped inside. For the first time in its life, the sun will be darkening instead of burning. It will be a remnant of what it once was. A white dwarf is an object of extremes. Although it is only as big as Earth, it holds about half the mass of the original sun. The matter inside it is packed so tightly that a single teaspoon would weigh tons. But what prevents it from collapsing further? The answer lies in quantum mechanics. Electrons, the tiny negative particles surrounding atoms, resist being squeezed into the same place. This resistance creates a new kind of pressure, electron degeneracy pressure, that keeps the white dwarf stable, even though fusion has long since ceased. It is a star held up not by fire, but by physics. Over trillions of years, the white dwarf will slowly radiate away its remaining heat, fading ever further into darkness. Eventually, it will become a cold, inert object known as a black dwarf, a theoretical stage of stellar evolution that no star has yet reached, because the universe itself is not old enough. But from beginning to end, the Sun's life cycle illustrates the profound forces that govern all stars, from gravitational collapse to nuclear fusion, and from brilliant radiance to quiet extinction. It is the story of transformation, violent, elegant, and ultimately inevitable. By studying our sun, we do more than uncover the fate of our own solar system. We gain a blueprint for the lives of countless other stars scattered across the galaxy. While some stars are larger and live shorter, more explosive lives, and others are smaller and burn for far longer, the same underlying physics applies. Hydrogen becomes helium, helium becomes carbon, and eventually, even the brightest star must dim. In the grand story of the cosmos, the sun's journey from light to silence is not the exception, it is the rule. And now that we have explored this path, it is time to step beyond it. After a star like our sun reaches the end of its life, what remains is not a fiery explosion, but a quiet ember, a white dwarf. This small, dense object is all that is left after the outer layers are blown away into space. No longer fueled by fusion, the white dwarf glows only because of the immense heat trapped inside. It is roughly the size of Earth, but with nearly half the mass of the sun packed tightly into its volume. At first glance, it appears peaceful. But beneath its still surface lies one of the most extreme and mysterious states of matter in the universe. So how can such a small object resist the crushing force of gravity without any fusion? The answer lies in a strange law of quantum mechanics. According to the Pauli exclusion principle, no two electrons can occupy the same quantum state at the same time. When gravity squeezes the atoms inside a white dwarf closer and closer together, the electrons begin to resist. This resistance creates a new kind of pressure, electron degeneracy pressure. It is not thermal. It does not come from heat or fusion. It is a purely quantum mechanical phenomenon, and it is powerful enough to hold up a star. But like all things in physics, there are limits. In the early 20th century, a young Indian physicist named Subrahmanyan Chandrasekhar calculated just how massive a white dwarf could be before even electron degeneracy pressure would fail. The result of his work became known as the Chandrasekhar limit. According to his theory, if the mass of a white dwarf exceeds roughly 1.4 times the mass of our sun, gravity will overwhelm the quantum pressure. The white dwarf will collapse, triggering a transformation into something even more exotic. At the time, Chandrasekhar's findings were controversial. Many leading physicists of the day, including Arthur Eddington, rejected the idea that there could be a maximum mass for white dwarfs. But as astronomical observations grew more precise, the Chandrasekhar limit was confirmed again and again. White dwarfs heavier than this limit simply do not exist. In binary star systems, When a white dwarf gathers material from a companion star and surpasses this threshold, it can trigger a thermonuclear explosion known as a Type Ia supernova, one of the brightest events in the cosmos. The Chandrasekhar limit marks a boundary in stellar evolution. Below it, stars can end their lives as stable white dwarfs. Above it, they must collapse into even denser forms, either neutron stars or black holes, depending on their mass. This limit is not just a number. It represents the tipping point between two fundamentally different outcomes: long, quiet cooling versus violent collapse. And it shows that even the smallest stars are governed by the same cosmic rules dictated by gravity, quantum mechanics, and the balance between them. In a way, white dwarfs are among the most poetic objects in the universe. They are the quiet remnants of once glorious stars, still glowing long after their fires have gone out. Yet, hidden within their tiny cores are the secrets of quantum physics and the thresholds of matter itself. Thanks to Chandrasekhar's groundbreaking work, we now know that white dwarfs are not infinite. They have a limit, and when that limit is reached, the universe does not forgive. It transforms them into something stranger. And that brings us to the next chapter in the life of dying stars, the birth of the neutron star. When a dying star exceeds the Chandrasekhar limit, it cannot remain a white dwarf. Gravity begins an unstoppable collapse, squeezing the core into something even more extreme. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos in the process. What remains is no longer an ordinary atom-based object. It is a single, immense nucleus, a neutron star. In this new form, matter reaches densities beyond imagination. A single teaspoon of neutron star material would weigh more than a mountain. This is one of the densest forms of matter known in the universe. But how can something so dense avoid collapsing into a black hole? Once again, the answer lies in quantum mechanics. Just as electrons in a white dwarf resist being compressed, neutrons do the same in a neutron star. This resistance is known as neutron degeneracy pressure. It is a powerful force born from the Pauli exclusion principle, which prevents identical particles from occupying the same quantum state. When neutrons are packed to the brink, they push back. This push is the only thing that prevents the neutron star from collapsing further into a singularity. The resulting object is unlike anything we can truly comprehend. A neutron star may be only about 20 kilometers across, roughly the size of a city. Yet it can contain more mass than the Sun. Its surface gravity is so intense that if you were to drop a pebble from just 1 meter above, it would hit the surface at several million kilometers per hour. Time slows near it. Light bends around it. And deep within, the state of matter may be so exotic that it no longer resembles any known substance on Earth. Neutron stars are not just dense, they are strange to the very core. These bizarre stellar remnants also possess extraordinary magnetic fields. Some neutron stars, known as magnetars, have magnetic fields trillions of times stronger than Earth's. These fields are so intense that they can distort atomic structures and generate powerful bursts of radiation. Others spin rapidly, emitting beams of electromagnetic radiation from their poles. When these beams sweep across Earth, we detect them as regular pulses, leading to the name pulsar. Some of these cosmic lighthouses rotate hundreds of times per second with clock-like precision. Despite their power, neutron stars also have their limits. If the mass of the core exceeds approximately 2 times the mass of the Sun, even neutron degeneracy pressure will no longer be enough. At this point, the collapse continues without end, forming a black hole. This theoretical boundary is known as the Tolman-Oppenheimer-Volkoff limit. It is the final threshold in the battle between quantum pressure and gravity. Beyond it, no known force of matter can resist collapse. The neutron star disappears, leaving behind only a region of warped space and time. Neutron stars represent a boundary in our understanding of the universe. They are born in death, forged in collapse, and sustained by the most fundamental laws of quantum physics. Yet, even they cannot last forever. As we approach their upper limits, we find ourselves staring into the abyss of black holes and wondering, could there be something beyond? Could matter behave in ways we have yet to imagine? As we will see in the next chapter, some physicists believe that stars even stranger than neutron stars may exist, and if they do, they may hold the key to some of the universe's deepest mysteries. There comes a point in the life of a star where all resistance ends. The fusion has stopped. The quantum pressures of electrons and even neutrons have failed. Gravity has won. When the collapsing core of a massive star exceeds the Tolman-Oppenheimer-Volkoff limit, there is no known force in nature strong enough to hold it up. The matter continues to collapse, not into a denser object, but into a singularity, a point of infinite density and zero volume. Around it, space bends so severely that not even light can escape. A black hole has formed. A black hole is not a solid object. It is a region of space defined by one key boundary, the event horizon. This is the surface beyond which nothing can return. Once crossed, all paths lead inward, toward the singularity. No signal, no photon, no particle can escape. From the outside, the black hole appears dark, invisible against the fabric of space, unless it interacts with nearby matter. As gas and dust spiral into its grip, they form an accretion disk that glows brightly, emitting intense X-rays and radio waves as they are heated to extreme temperatures. Black holes come in many sizes. Some are just a few times more massive than our Sun, the remnants of collapsed giant stars. Others are monsters that lurk at the centers of galaxies, containing millions or even billions of solar masses. These supermassive black holes shape the structure and evolution of galaxies themselves, anchoring the motion of stars in vast spiral arms. Despite their immense power, black holes obey the same laws of physics as the rest of the universe. They are not magical. They are inevitable consequences of gravity pushed beyond its final limit. But for all we know about black holes, there is much we do not. The singularity at the center defies our current understanding of physics. It is a place where the equations of general relativity break down, and quantum mechanics offers no clear solution. Some theories suggest that a new form of quantum gravity may one day resolve the mystery. But for now, the heart of a black hole remains hidden behind the veil of the event horizon. It is a cosmic secret we may never see directly, only infer through the effects it has on the matter and energy that surround it. Perhaps most fascinating of all is that black holes are not entirely black. In the 1970s, physicist Stephen Hawking showed that black holes can emit a faint glow, now known as Hawking radiation. This arises from quantum fluctuations near the event horizon, where particle-antiparticle pairs form. One falls in, while the other escapes, slowly draining energy from the black hole. Over unimaginable timescales, this process could cause black holes to shrink and eventually vanish. Even the most powerful structures in the universe may not be eternal after all. So, what lies beyond the black hole? Is it truly the end, a place where space and time are crushed into a point? Or could there be something more? Another state of matter, another structure of space, waiting on the other side? The notion of black holes as singularities is a prediction, but one born of incomplete knowledge. Some physicists believe there may be alternatives, stars that appear to be black holes, but are not. Stars that resist collapse through mechanisms we have yet to understand. And in the next part of our journey, we will begin to explore those bold and exotic possibilities. At first glance, black holes appear to be the inevitable endpoint for massive stars, a collapse so complete that nothing can escape. But what if there is another path? What if, somewhere between neutron stars and true black holes, lies a realm of objects supported by forms of matter even stranger than anything we have observed? This is where the idea of exotic stars begins. Not made from ordinary atoms or even from neutrons, these stars are theoretical constructs, imagined by physicists who dared to question whether gravity always wins in the same way. The central question is deceptively simple. Could there be another form of pressure strong enough to counter gravity, even when the core becomes denser than a neutron star? The answer depends on the nature of the matter inside the object. Ordinary matter generates positive pressure, an outward push that resists gravitational collapse. But some hypothetical forms of matter could exhibit negative pressure in certain regions. Negative pressure does not push outward. It pulls inward, or in some cases, behaves in ways that defy classical intuition. And this opens a portal to entirely new possibilities. One of the earliest to explore these possibilities was the physicist Hans Adolf Buchdahl. In the year 1959, he derived a mathematical limit that any realistic star must obey. According to Buchdahl's theorem, No stable star made of conventional matter with positive energy density and positive pressure could be smaller than 9/8 of its Schwarzschild radius. This radius is just above the event horizon of a black hole. In other words, real stars must remain slightly larger than black holes. But what happens if the matter inside is not realistic? When physicists began exploring models with exotic equations of state, those that allow pressure to become negative or vary in complex ways, Buchdahl's limit no longer applied. Suddenly, it became possible to imagine stars that were almost indistinguishable from black holes. These objects could be just slightly larger than their Schwarzschild radius, compact enough to mimic a black hole's gravitational field, but without an event horizon. They could emit light, information, and radiation, subtle signals that might allow us to tell them apart from true black holes if we look closely enough. These hypothetical stars are not just theoretical curiosities. They have forced astronomers and physicists to reconsider what we mean when we observe a black hole candidate. When we detect the merger of two ultra-dense objects or spot something massive at the center of a galaxy, we must now ask, is it really a black hole, or could it be an exotic star? These compact imposters challenge one of the most iconic predictions of general relativity, and they demand that we test the universe not just for what it appears to be, but for what it might secretly contain. As we move forward, we will explore one of the most compelling candidates in this exotic category, a theoretical object known as a gravitational vacuum star, or gravastar. It is built not from particles or plasma, but from pure vacuum energy, stabilized by layers of negative pressure. In many ways, it resembles the behavior of dark energy itself, and if such objects exist, they could radically change our understanding of black holes, the nature of space-time, and even the acceleration of the universe. The next chapter of our journey will take us to the heart of this strange and fascinating idea. Before diving deeper into the realm of exotic stars, we need to examine a critical boundary in the physics of compact objects, one that defines the very edge of what a realistic star can become. This is known as the Buchdahl limit. In the year 1959, physicist Hans Adolf Buchdahl derived a mathematical constraint based on Einstein's general theory of relativity. He proved that for any spherically symmetric star made of conventional matter, with positive energy density and pressure, there exists a minimum size below which the star cannot remain stable. This minimum size is not arbitrary. According to Buchdahl's result, a realistic star cannot have a radius smaller than 9/8 of its Schwarzschild radius. The Schwarzschild radius, as you may recall, is the size an object must be compressed into for it to become a black hole. Buchdahl's limit tells us that even the most compact star made of normal matter must be noticeably larger than that. In simpler terms, if an object is smaller than 9/8 of its Schwarzschild radius, it cannot be a star at all. It must be a black hole. There is no middle ground within classical physics. This constraint has powerful implications. It means that no matter how strange or dense a star becomes, as long as it is composed of realistic matter, it must always stop short of becoming indistinguishable from a black hole. It is this gap, the difference between a black hole and a nearly black object, that allows astronomers to search for observational signatures. The Buchdahl limit gives us a theoretical foundation to distinguish stars from black holes based on size alone, offering a testable prediction rooted in the known laws of physics. But here is where things get interesting. The Buchdahl limit only applies to stars with positive pressure and energy density throughout their interior. If a theoretical star violates this condition, say by having regions of negative pressure, then the limit no longer holds. The object could, in theory, be even more compact than Buchdahl's boundary, approaching the very radius of a black hole without ever crossing into one. This loophole opens the door to an entirely new class of compact stars, ones that could hide in plain sight, looking just like black holes from the outside. Understanding the Buchdahl limit is essential for grasping how radical the concept of exotic stars really is. It is not just about finding new types of matter or challenging old assumptions. It is about stretching the boundaries of what space, time, and mass can physically allow. When we explore the possibility of Grava stars and other exotic objects, we are not just imagining science fiction. We are testing the very framework of general relativity itself. And as we shall soon see, that framework, while elegant and robust, may not be as final as it once appeared. Imagine a star so compact that it hovers just above the boundary of becoming a black hole, so small that its surface sits just outside its Schwarzschild radius. And yet, unlike a black hole, it possesses no singularity and no event horizon. This is the idea behind a Grava star, a gravitational vacuum star. Proposed in the early 2000s as an alternative to black holes, the Grava star is a hypothetical object held together not by conventional matter or nuclear pressure, but by an exotic form of energy with negative pressure, mimicking the behavior of dark energy. At its core, a Grava star contains something profoundly strange, a region of space filled with vacuum energy. Vacuum energy is a quantum concept describing a state where even empty space is teeming with fluctuating fields and potential energy. What makes this core unusual is not just that it has energy, but that it exerts negative pressure. That negative pressure pulls inward with the same intensity that its energy density pushes outward. The result is balance, a perfect internal symmetry that produces no net gravitational force. Inside this vacuum bubble, gravity cancels itself out entirely. Surrounding this vacuum core is a thin shell of ultra-dense matter, often imagined as a crust made of stiff, exotic material. This shell replaces the singularity and the event horizon found in traditional black holes. It is the boundary where the vacuum pressure inside meets the gravitational field outside. This structure allows the Grava star to remain stable, despite having no internal fusion and no true surface in the traditional sense. Light and matter could, in theory, bounce off the outer shell instead of disappearing forever, making gravastars fundamentally different from black holes. Mathematically, gravastars are permitted by the Tolman-Oppenheimer-Volkoff equations, the same equations that describe neutron stars, but only if one allows negative pressure to play a role. In fact, the most stable configuration occurs when the negative pressure in the vacuum core exactly equals the positive energy density, maintaining constant values throughout the interior. This specific balance gives rise to something that behaves like a false vacuum, a state of space-time that resists further collapse, not through mass, but through geometry and field dynamics. One of the most remarkable properties of gravastars is what happens to gravity inside them. Because the inward pull from positive energy and the outward push from negative pressure cancel out, there is no net gravitational force in the interior. A spacecraft or observer inside such an object, assuming they could somehow survive the transition through the shell, would feel no gravitational pull in any direction. They would float, not because of weightlessness, but because gravity itself has vanished within the boundary of vacuum energy. It is a region of perfect balance, an artificial equilibrium of space. Gravastars are not just theoretical oddities, they raise profound questions about what black holes really are. Could some of the black holes we have observed actually be gravastars in disguise? Could the vacuum energy inside them be related to the mysterious dark energy accelerating the universe? And if gravastars are real, do they mark a deeper, hidden structure to space-time that we have only begun to glimpse? These questions take us beyond the edge of known physics, toward a place where stars, fields, and geometry blur into something altogether new. And it is there our journey will continue. If you could somehow journey past the shell of a gravastar and enter its interior, what you would find is unlike anything in the known universe. There would be no solid surface, no swirling gas, no stormy plasma. Instead, you would be inside a region dominated entirely by vacuum energy, a smooth, uniform field of space itself, perfectly still, yet full of potential. But what truly sets this environment apart is that within the gravastar, gravity vanishes. The opposing effects of energy density and negative pressure cancel out completely. There is no up or down, no weight, only equilibrium. This perfect cancellation creates a place that feels less like the core of a star and more like an engineered bubble of nothingness. You would not fall. You would not float upward. You would simply be suspended in a state of gravitational neutrality. It is a region where space-time curves so precisely that all internal forces balance out. In contrast to the crushing densities of neutron stars or the infinite singularity of black holes, the interior of a gravastar is tranquil, stable, and strangely serene. It is not filled with matter, but with a kind of structured void. But this does not mean the gravastar is empty in the classical sense. Vacuum energy, by definition, contains energy. It is not zero, even if it appears invisible. In fact, it is this energy that generates the negative pressure required to keep the gravastar from collapsing. According to general relativity, pressure contributes to gravitational fields just like mass does. However, negative pressure does the opposite of what we expect. It pushes outward, repelling gravity instead of enhancing it. The result is an internal field that neutralizes all gravitational pull from within. Another fascinating property of this environment is its uniformity. Inside a gravastar, both the energy density and the pressure are constant from the center all the way to the inner edge of the shell. There are no gradients, no hotspots, no turbulence. In this way, the interior of a gravastar resembles the hypothetical vacuum state of the early universe, smooth, flat, and filled with latent energy. Some theorists even speculate that this connection might hint at deeper links between gravastars, inflationary cosmology, and the nature of dark energy itself. Of course, all of this remains purely theoretical. No one has ever traveled inside a gravastar, nor are we even certain they exist. But the physics that describe them is grounded in our best models of space-time, pressure, and energy. If real, gravastars would represent not just a new class of celestial object, but an entirely new way for nature to organize matter and structure itself. They offer a glimpse into a frontier where geometry becomes as real as mass, and where the fabric of the cosmos is not just a backdrop, but a force in its own right. From a distance, gravastars and black holes appear almost identical. Both are incredibly compact. Both warp the space around them so severely that light bends dramatically in their presence, and both can sit quietly in the hearts of galaxies or flare to life during violent cosmic collisions. So how can we possibly tell them apart? The answer lies in one defining feature: the event horizon. A black hole has one. A gravastar does not. That difference may be subtle in theory, but it could leave behind observable clues, if we know where and how to look. The event horizon is the boundary beyond which nothing can escape. Not light, not particles, not information. Once something crosses it, it is lost to the universe forever. In contrast, gravastars have no such boundary. While they may be nearly as compact as black holes, their surface lies just outside the critical threshold. That means, in principle, they could reflect or emit faint signals from just beneath the surface, signals that would be impossible for a true black hole. These small leaks of light or radiation could be the first sign that something more exotic is hiding in plain sight. But there is another, even more promising way to tell them apart: gravitational waves. When two massive objects spiral into each other and merge, they send ripples through the fabric of space-time. These gravitational waves, detected by observatories like LIGO and Virgo, carry information about the mass, spin, and structure of the colliding objects. For black holes, the gravitational wave signal fades in a very specific pattern after the merger. If a gravastar is involved instead, the signal may echo, oscillate, or ring slightly differently, subtle differences, but measurable with enough precision. Physicists have proposed that these so-called echoes might be the key. In a black hole merger, once the event horizon forms, all disturbances are swallowed. But if a gravastar replaces one of the black holes, there is a hard surface, not a horizon. Waves could bounce off this surface and reflect back outward. These reflected waves would arrive milliseconds after the primary signal, creating tiny echoes that ripple through the data. Detecting such echoes would not only challenge the black hole model, it would point directly towards something new, something we have never seen before. So far, the search for gravitational wave echoes has produced intriguing but inconclusive results. Some analyses suggest faint hints of echoes in certain merger events, while others argue that the data are consistent with classical black holes. The truth is, our instruments are only now reaching the sensitivity needed to test these ideas. As observatories become more advanced, and as more mergers are recorded, we may finally gather enough evidence to confirm or rule out the existence of gravastars. The future of this search is as exciting as it is uncertain. In the end, the question is not only whether gravastars exist, but what their existence would mean. They would be a striking reminder that not everything in the universe fits into neat categories. They would force us to rethink the meaning of collapse, the nature of horizons, and the fate of matter under extreme conditions. More than anything, they would show us that the cosmos is still full of secrets, that even in the shadows of black holes, something new might be waiting to be discovered. And perhaps, in that discovery, lies the next revolution in our understanding of space and time. It may sound like science fiction, an object so compact that it mimics a black hole, yet is filled with vacuum energy instead of a singularity. But the idea of gravastars becomes even more fascinating when we consider their potential link to something far larger: dark energy. The mysterious force driving the accelerated expansion of the universe remains one of the greatest puzzles in cosmology. We know what it does, but we do not know what it is. And now, some physicists are beginning to wonder, what if dark energy is not spread evenly through space, but clumped inside gravastars? At the heart of a gravastar lies vacuum energy with negative pressure, exactly the same properties attributed to dark energy on a cosmic scale. This has led researchers to ask a provocative question: could black holes, or what we think are black holes, actually be repositories of dark energy? In 2023, a study from the University of Hawaii made headlines by analyzing supermassive black holes in distant galaxies. The team discovered that over time, these objects seem to grow in mass at a rate consistent with how dark energy is believed to evolve as the universe expands. The implication was startling. If the mass of these black holes increases in tandem with cosmic acceleration, it may mean they are not conventional black holes at all, but rather gravastar-like structures composed in part of vacuum energy. In that case, What we have been calling dark energy might not be an invisible field spread thin across the universe. It might be hidden inside millions of compact objects scattered throughout space. This idea is not only bold, it is radically different from how most cosmologists have been trained to think about energy, gravity, and expansion. Naturally, such a claim has sparked intense debate. Critics argue that the observational data could have alternative explanations, or that the theoretical framework lacks the rigor needed to replace the standard cosmological model. Others question how vacuum energy could remain stable inside such objects without tearing them apart or causing uncontrolled inflation. The mathematics behind these gravastar dark energy connections is still evolving. For now, there is no consensus, only a lively and growing conversation that challenges long-held assumptions about the structure of the universe. Yet, even in the face of uncertainty, the idea persists. Perhaps dark energy is not a passive background field, but a dynamic phenomenon shaped by astrophysical processes. Perhaps gravastars are not merely alternatives to black holes, but key players in the evolution of the cosmos. If so, then each merger we observe, each compact object we measure, is not just a test of general relativity. It is a data point in the search for the true nature of the universe's expansion. Gravastars may not just mimic black holes, they may help power the very fabric of cosmic growth. For now, gravastars remain theoretical, and their link to dark energy is speculative. But speculation has always played a role in scientific progress. It is how Einstein imagined curved spacetime before it was confirmed. It is how quantum mechanics emerged from paradoxes. Perhaps, one day, we will look back at gravastars not as curiosities, but as the first glimpse of a deeper truth, that black holes are not what they seem, and that the force accelerating the universe may be locked away in their silent cores. Until then, the mystery remains, and so does the wonder. For over a century, black holes have been regarded as the ultimate endpoints of gravitational collapse, the places where matter, time, and even the laws of physics reach their limits. They are written into the equations of general relativity. They define our models of galaxy evolution, high-energy astrophysics, and cosmic entropy. But what if we have been wrong? What if the universe has fooled us? If black holes do not truly exist and are instead exotic stars, gravastars, or something stranger, then we have misunderstood not just a class of objects, but the very nature of space and time. This is not merely a correction of terminology. If black holes are illusions, mimics rather than singularities, then the implications cascade through every field of physics. Our understanding of quantum information, gravitational entropy, and even the beginning and end of the universe would need to be rewritten. The information paradox, once tied to the fate of data inside a black hole, would take on a new form. What we thought were voids in space might be engines of cosmic structure. The vacuum itself may have a shape, a role in evolution we never suspected. It forces us to ask unsettling questions. If we were wrong about black holes, what else have we misunderstood? Are there other cosmic illusions, objects that imitate what we expect, but are built from unfamiliar laws? Are the deepest truths of the universe accessible through mathematics alone, or must they be felt in the data, teased from light and waves across billions of light years? The Grava star hypothesis is more than a scientific proposal. It is a philosophical challenge. It reminds us that even our most confident theories may one day dissolve beneath a deeper understanding. In the end, black holes, real or not, serve a powerful purpose. They pull at the boundaries of our knowledge. They humble our certainty. And perhaps that is their truest form, not cosmic monsters, but cosmic mirrors, reflecting back our own search for meaning in the void. If Grava stars replace them, they do not diminish the mystery, they deepen it. And in doing so, they invite us to keep asking questions, not only about what the universe is, but about how much more of it there is still left to discover. From the first flickers of nuclear fire to the quiet shadows of white dwarfs, from the collapsing hearts of massive stars to the speculative boundaries of Grava stars, our journey through the lives and afterlives of stars has revealed more than just how matter behaves. It has shown us how ideas evolve. What begins as a calculation on paper can grow into a theory, and then into a question that challenges everything we thought we understood. In the end, stars are not just light in the sky. They are tests of reality, burning with mystery, pressing us toward deeper truths. We have explored the limits of quantum pressure, traced the delicate balance between collapse and stability, and questioned whether black holes are truly the end or only a beginning. Along the way, we encountered stars made of neutrons, stars without fusion, stars filled with vacuum energy. And now, even familiar giants like Betelgeuse remind us that the universe still holds surprises, even in places we have watched for centuries. The cosmos does not simply repeat itself. It reinvents its own rules, quietly, patiently, just beyond the edge of what we can see. In many ways, the stars we cannot see, the ones built from theory, from mathematics, from bold imagination, are just as important as those we can. They force us to ask not only what is out there, but what is possible. Are Grava stars real? Is dark energy hiding inside collapsed stars? Could the most terrifying objects in the universe turn out to be elegant illusions? We do not yet know. But what matters is that we are still asking, still listening, still refining the shapes of what might be. In science, mystery is not an obstacle. It is a compass pointing forward. So the next time you look up at the night sky, let your eyes rest not just on the brightest stars, but on the darkness between them. Somewhere in that darkness, a Grava star might be waiting. A neutron star might be spinning. A supernova might be preparing its final breath. The universe is not finished writing its story, and neither are we. Thank you for joining me on this journey through the strangest stars in the cosmos. If you found wonder in what we explored together, there is much more to come. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.